Assignment 6.
Can you tell me the question?
Last question. Yeah, I can read it out.
Sure. Please read.
It says, consider a linear transformation T such that R3 from R3 defined by Tx is equal to Ax, where A is a 3 by 3 real matrix. Uh, then there are 4 options there. Can you please see it in your screen so that you will see all the options?
What was the question? Can you tell me briefly?
Yeah, it is saying then if A is orthogonal, then T is an isometry, but not conversely. And second option is T is an isometry. Then A is orthogonal, but not conversely. Then third option is if A is orthogonal, if and only if T is an isometry.
Okay.
And then there's a relation between A orthogonal and T being isometry.
Isometry means it is actually norm preserving. So norm of Tx, you need to see that if it is norm of x. Now you can check that. So you
Yeah,
need to check that which option is working for this.
actually, I tried to solve it, and as per solving, I got that if A is orthogonal, then T is an isometry
Yes,
because,
it is right.
yeah, but the answer which is marked in the correct answer is something else in this, the which is marked in the answer
Uh,
sheet.
what was another answer?
It is marked A is orthogonal if and only if T is an isometry, but actually T become an isometry because A is orthogonal. It's reverse, right?
Uh, uh, yes, T orthogonal.
So answer is if
This imply T is isometry. It is true because you can use.
A is orthogonal, imply T isometry.
Okay, are you saying about the converse?
No, no, like you have written T orthogonal, right? So I've just
Yes.
said it's A is orthogonal.
Yes. A is orthogonal, then T is isometry. Yes.
And the answer which is marked as correct is uh, A is orthogonal if and only if T is an isometry, meaning T is isometry, then A is orthogonal.
What about the converse part? So T is isometry.
Will I give you the link of the?
Actually, you can use this factor. And so norm of T, it is actually same as norm of A, and inner product x comma x. This is actually same as A transpose AX and X, and this is actually A transpose A is orthogonal if we assume A orthogonal, then A transpose A is identity, and if you use this is identity matrix, then we are getting x comma x, which is same
Yeah,
as norm x square, and
yeah,
this is the norm of s square. So we are getting uh, orthogonal imply norm of tx. This is actually same as norm of x. We are getting that. But what about the reverse? So reverse is also right, isn't it? Hmm.
no, I mean if T is an isometry, no, it is saying that A will be orthogonal only
Yes.
if T.
Even if T is not isometry, uh, can A be non-orthogonal?
Mm,
Okay, I need to think about that. It is not clear. for now.
Yeah. Shall I give you the link of the quiz?
Okay, we may discuss next day. Okay.
Okay, sure.
I think reverse can also be proved from this. I don't know for now. So let us discuss those topics. So we'll discuss about eigenvalues, and another interesting thing is eigenvectors, and then characteristic polynomials. Polynomial. Many times there is another synonym for eigenvalues or eigenvector, that is characteristic values or characteristic vectors. Okay, so those will be our topic of discussion. What is eigenvalue? So suppose T is a linear transformation from V to V, then if there exists some C, suppose there exists some C such that instead of C, let us denote it by lambda from the field F, such that Tx equal to lambda x. This relation is holding for some non-zero x. Okay. So here x is from V. X belongs to the vector space V. Then we will call lambda an eigenvalue. If this relation is holding for some non-zero x, then we will call lambda is an eigenvalue of the transformation T. Okay. So then what is eigenvector? A non-zero vector corresponding to this lambda, that is a non-zero vector x corresponding to this lambda, that is this x satisfies this relation. T of x is same as lambda x. Then we will call x to be an eigenvector. X is said to be an eigenvector. Eigenvector with respect to lambda. So this is the definition of eigenvector. So let us see an example, then it will be clearer. So consider the rotation. Okay, T from R2 to R2. Instead of rotation, let us take this example, x comma y, apply T, it projects, so it will be 1 0 0 1 0 0, and here x comma y, that is this is same as x comma 0. Okay, consider this transformation. I have written in column form, but you can write it in row form, that is x comma y, a order pair. So let us see what is an eigenvector for this transformation. What this transformation is doing, it projects a vector. Suppose x is a vector 2 comma 3, this vector, this will be projected on x-axis. So tx will be this vector, right? It is now 2 comma 0. So now you can see from the picture there exists some vector for which t acts as stretching. Okay. For example, if you consider any vector from x-axis, then projection is same thing, right? Projection is also that same vector. T of x comma 0, by definition, this is same as not x comma 0. We have written in column form. So T of x comma 0, this is same as x comma 0. That is, on x-axis, every vector is stretched by 1. The factor is 1 here. Okay. So here t of x comma 0 is 1 into x comma 0. So you can say that any vector from the x-axis, that is, for example, an example will be 1 comma 0. This is an eigenvector, and actually this is same as 1 times 1 comma 0. So here this is t, this is x, and this is lambda times that x. So here 1 is an eigenvector, 1 is an eigenvalue, and this 1 comma 0, this is an eigenvector corresponding to this scalar c, this scalar 1. Okay. So eigen, you can thought eigenvalue as stretching factor. Okay. So there are some vectors for which t acts as stretching. So those stretching factors are called eigenvalue, and those vector which on which t acts as stretching, those vectors will be called eigenvector corresponding to that stretching factor. Okay, this is the motivation. So this is really very helpful for understanding many different type of linear transformations, because you can some with respect to some suitable basis, the linear transformation will be some will be in a some beautiful form because of this fact. Okay, let us consider another vector. So you can see that every vector on x-axis is actually eigenvector, and you can also see that every vector on y-axis. For example, consider this thing, t of 0 comma 2. By definition, it is projection on x-axis, so this is actually 0 comma 0, and you can write 0 comma 0 as 0 times 0 comma 2. So you can see that every vector on y-axis is stretched by 0. 0 is the stretching factor. So from here, the observation is 1 and 0, those are eigenvalues. Okay, and corresponding to 1, every vector of this form x comma 0, okay, those are eigenvalues, eigenvectors, and corresponding to 0, every vector of this form 0 comma y is an eigenvector. Note that eigenvector is always non-zero. Okay, you should remember this. X is any non-zero scalar, y is any non-zero from real number. So those are the eigenvalues and eigenvector corresponding to this transformation. So we have considered this projection. Let us consider another transformation, that is rotation. For rotation, if you see, suppose rotation by some non-negative angle. Okay, rotation with an angle theta, and theta is non-zero. Then every vector, so this x and y axis will move to this new x and y axis. So suppose theta is 30 degree. Now you can see that if you pick any vector from this plane, this will move to another vector, and the angle between them will be 30 degree, right? So this their angle between them will be 30 degree. So from here you can observe that every vector, there is no vector which is stretched by the transformation except 0, because if you rotate 0 comma 0, this origin, it will be again 0 comma 0. But this is not interesting because we are not considering 0 as eigenvector. Okay, so for this rotation, there is no real eigenvalue. And if we are considering the field R, then there is no eigenvector also. Okay, because you can see that any vector in the plane, this will be shifted. So there is no vector which is stretched by the transformation. So there is no eigenvector. Let us see another example. We have done rotation. So reflection. Let us check this example. Reflection is given by t of x comma y. This is same as y comma x. Reflection, that is reflection around this line. So any point x comma y, this vector, x comma y, this vector, this will go to this vector by the transformation if you apply t. So this is the reflection. So now again you can see that for this transformation, every vector on this y equal to x on this line, for example, take 1 comma 1. If you apply t, this is same as, by definition, it is same as 1 comma 1 because it is switching x and y. So it is actually same as 1 times 1 comma 1. So every vector on this x equal to y line are fixed. Okay, so they are staged by the factor 1. So here scaling factor is 1, so 1 is eigenvalue, and eigenvector is will look like this. Any vector on the line x equal to y, where x is non-zero, because we are not considering 0 comma 0, the 0 vector, to be eigenvector. We are not considering that. Okay, so any vector of this form will be an eigenvector. So let us check an example. Consider this question. Find the eigenvalue, sorry for that, and eigenvector for this matrix 2, 3, minus 1, 1. Note that we can define eigenvector of a matrix. Okay, so we know that for finite dimensional case, any transformation has some matrix representation. So we are assuming this corresponding to A, we have this transformation Tx equal to x. We can define this transformation. So eigenvector of A, this is actually defined to be eigenvector of this transformation. Okay, so this is the definition of eigenvector. So let us, before computing that, let us check an interesting way to compute eigenvalues and eigenvectors. So consider Tx equal to x. If lambda be an eigenvector, so when lambda will be eigenvalue, sorry, lambda is from scalar. If lambda is an eigenvalue, this will happen if there exists some non-zero, there exists x which is non-zero vector, or v is denoted by v, such that t times v is same as lambda times v, right? And this is same as, since we are considering those type of transformations. So this will be same as A times B is same as lambda times B, and this will be if and only if we can write it as A minus lambda I times B equal to 0. So if and only if A minus lambda I times X, this is actually matrix, and this is also matrix of this form x1 up to xn. Okay, so here A is n cross n matrix, we are considering that, and if and only if this is actually, this system has a non-zero solution. So when does a system has non-zero solution? We know this is true if and only if determinant of A minus lambda I equal to 0. This criteria will be helpful to find an eigenvalue, because to check if something is eigenvalue or not, we'll put into the determinant and we need to check determinant vanishes or not, right? So let us return to this question. Here we need to find eigenvalue for this 2, 3, minus 1, comma 1. Is same as 2, 3, minus 1, comma 1. So let lambda be an eigenvalue. Then we need to check when the determinant, this is if and only if determinant of A minus lambda I equal to 0. Now if you write the determinant, this is what is A minus lambda I? From here you can see that A minus lambda I, this is actually same as 2, 3, minus 1, 1 minus lambda times 1, 1, and this is diagonal. So this is actually 2 minus lambda and 3. Here it is minus 1 and here it is 1 minus lambda. So you need to subtract from the diagonal. Okay. So this is same as saying 2 minus lambda, 3 minus 1, 1 minus lambda. This determinant actually 0. And this is same as 2 minus lambda into 1 minus lambda minus 3 times minus 1 equal to 0. Now let us do some multiplication. It will be 2 minus 2 lambda minus lambda plus lambda square plus 3. This is same as 0. If and only if lambda square minus 3 lambda plus 5. This is actually 0. So what will be the solutions?
A complex number.
Okay, let us do that. This is minus of minus 3, that is plus 3, plus minus root over b square, which is 9 minus 4 AC, that is 4 times 5 by 2. So there, yes, you are right. The solutions are complex number plus minus root 21 times I by 2. So those are the eigenvalues. So from the previous geometry, this eigenvalue cannot be obtained because you can see that eigenvalue is now a complex number. Okay. So for this, the field is everywhere field is assumed to be complex number if it is not given. Okay, field is C. So those are the eigenvalues. One eigenvalue is 3 plus root 2 21i by 2, and another is 3 minus root 21i by 2. You can now you can see why this thing actually important, because you can easily you can figure out any eigenvalues from this formula. You don't need to do anything else. Okay. Now we need to find eigenvector for this matrix set. So here it will be very difficult, but let us do this. Corresponding to lambda equal to 3 plus root 21 I by 2.
Sir, 9 minus 20, I think it will be 11 in the
Okay,
root.
sorry for that.
No problem.
Well, yes, thank you. So it is 11 by 2. Corresponding to lambda, let us find an eigenvector. So eigenvector will satisfy this relation, right? A minus lambda I times x. This is actually 0 because those are equivalent steps. So let x belongs to R n cross 1 be an eigenvector. Then this will give a minus this lambda I times x equal to 0. Okay, we need to solve this matrix equation, and we know how to solve this equation. This is very easy, because if you put we have already computed a minus lambda I. So this is actually 2 minus lambda, 3 minus 1, 1 minus lambda. This is the coefficient matrix. Let us denote it by some c. This is actually same as this matrix. So if you do row reduction, then this will be 2 minus lambda, 3, and there will be some. So you can reduce this actually, because the fact is that there will be some non-zero solution. So non-zero solution only possible if the rank is not 2. Okay, so if you row reduce, then with some suitable scalar, if you do this step R2 plus some scalar, suppose k times R1, then the second row will be 0. Okay, so now if you divide it, then the final row reduction will be 2 minus lambda by 3 and 1. And the next thing is 0 0. Therefore now you know how to solve this. Sorry, here it is actually 1, and here it is 3 by 3 by 2 minus lambda, because 2 minus lambda is non-zero. From here you can see that 2 minus lambda is non-zero. So what will be an eigenvalue? Eigenvector solution of Cx equal to 0. This is given by, what will be an solution? It is second thing is, you can see that second column does not contain any pivot. Okay, first column contain this. So from here you can choose the second column to be any free thing. Then this will imply the first thing will be, because this is actually equivalent to Cx equal to 0. This is actually equivalent to this. Actually x is this type of thing, x1 comma x2, right? So this cx equal to 0, this thing is equivalent to x1 plus 3 by 2 minus lambda x2, this is actually 0. So if you choose x2 to be 1, then x1 will be minus 3 by 2 minus lambda. So general solution is given by this times some scalar. Okay, C is any non-zero real number. Let us instead of denoting it by C, let us denote it by some L. L is any non-zero real number. So those are the eigenvectors. Okay, if you put the value of lambda, you will get some some complex number, actual complex number, and the eigenvector will look like this. Let us check another example, then it will be clearer. Given A is 1 1 1 1, we need to find eigenvalues, and another thing is eigenvectors. So let lambda be an eigenvalue. Then this is same as det of A minus lambda I. This is actually 0. Determinant of A minus lambda is 0. So we know that this is actually same as 1 1 1 1. Then subtract from the diagonal. Determinant of this actually 0. This is the notation. This is same as 1 minus lambda square minus 1. This is actually 0. From here, solving this, we are getting 1 minus lambda. This is actually plus minus 1. And this is equivalent to saying for plus 1, we are getting lambda equal to 0. And for minus 1, we are getting lambda equal to plus 2. So those are the solutions. Okay. Therefore, the eigen values are this set 0, 2. Or other way, sorry. Those are the eigenvalues 0, 2. Now let us find eigenvector. Eigenvector corresponding to 0, lambda equal to 0. So what will be eigenvector? Let x, which is same as x1 comma x2, this is an eigenvector. Then eigenvector will satisfy this relation, right? And this relation is same as A minus lambda I times x equal to 0. And we already know what is A minus lambda I. We have, this is actually this 1 minus lambda, 1 minus lambda, and 1 1 1 minus lambda. But here lambda is 0, right? So if you put 0, this will be the equation. This times x1 x2 is 0. So this is same as saying x1 plus x2 equal to 0, and another equation is x1 plus x2 equal to 0. So the second equation is redundant. This is same as x1 plus x2 equal to 0. Therefore, solution to the system, this system is given by x2 is free, right? So x2 is free, you can choose anything here, choose k, and then x1 from this relation, we are getting x2 to be minus k. If you assume, sorry, let x1 equal to k, any real number, then we are getting x2 equal to minus k. Okay. So instead of real number, we can take complex number, because we'll assume the field to be complex if nothing is given. So this will be the solutions. Okay, where k is any real number. But from these solutions, the eigenvalues, eigenvectors are minus k, that is, this is same as this, but where k is, now you cannot take k to be 0. So where k is any non-zero real number. Okay, this is how we find eigenvalues or eigenvectors. So let us check what will be an eigenvector corresponding to 2. So here we'll put lambda, value of lambda is 2. Okay, corresponding to lambda equal to 2. This is actually same as a minus lambda I times this x. This is 0, and this is same as 1 1 1 1. Now lambda is 2, so this is minus 2 here. This times x1 x2 is 0. Again, this is equivalent to minus x1 plus x2 equal to 0, matrix multiplication. The second equation is redundant, so choose x1 equal to k, then we are getting x2 equal to also k from this equation. Okay, therefore any solution to this system is given by this k comma k. K is any complex number or any real number, whatever is given, and therefore eigenvectors are again k times 1 comma 1, but now you cannot choose k to be 0, because eigenvectors are always non-zero. Okay, so this is how do we find, and this is the process of finding an eigenvectors. Okay. We have used this polynomial here for finding an eigenvectors, or sorry, eigenvalue. We are using this type of polynomial, this type of equations. Okay, or this equation is same as actually this equation, and those equations are called characteristic equation. Characteristic equation. Okay, this is the characteristic equation, and this polynomial determinant of lambda I minus a, opposite of that, this is actually polynomial of lambda. Instead of lambda, let us write x, then it will become polynomial of x, that is some combination of x to the power n up to x to the power 0. Okay, that is this type of thing, some equation of x, a polynomial. Then this polynomial, this is called actually characteristic polynomial. Okay, so for this question, characteristic equation is this. This is characteristic equation, and characteristic polynomial is actually this part. Lambda, instead of lambda, let us write x, then it will be x square minus 3x plus 5. This is the characteristic polynomial for this particular matrix. Okay, let us see some example. Before example, let us see an criteria. So we know product of eigenvalues. This is actually same as determinant of this matrix. Okay, so given a matrix A, the product of the eigenvalue, the notation is product of lambda I. This is actually same as is n by n matrix. This is actually same as determinant of A. Okay, so how do we see this? So proof, the short proof will be like this. Eigenvalues are given by this equation, right? Eigenvalues are given by this equation, precisely this equation. Determinant of A minus xi, this is same as 0. Now, if lambda i's are eigenvalues, then you can write this thing. This is actually same as lambda 1 minus x, lambda 2 minus x, up to lambda n minus x. Okay, let lambda i's are eigenvalues. Okay, so because lambda is also satisfies this polynomial, and if you compare, then these two left hand sides are same. Okay, so we are getting product of lambda I minus x I equal to 1 to n. This is actually same as determinant of A minus xi. We are getting this equality. Okay, now put this is actually equality, and you can put x any real number or any number from the field. So put x equal to 0. Okay, since this is identity, we are getting determinant of A. Putting x equal to 0 right hand side, we are getting this is product of lambda. From here you can conclude that product of the eigenvalues is actually determinant of that matrix. For example, you have seen that for this question, what is the determinant? Determinant is 1 minus 1, that is 0. And now check the product. Product of the eigenvalues 0 and 2, this is actually also 0. So from here you can verify this property. Okay. And there is another property which says sum of the eigenvalues, or notation sum of the lambda i's. This is actually same as trace of the matrix A. Okay. You can check this property also.
Sir, one question.
Yes.
In the box, we have that equation in the yellow box.
Yes.
So when we are saying determinant of A minus xi,
Yes.
determinant, can we make it distributive? Can we say determinant of A minus xi is equal to determinant of A minus determinant of
No,
x?
this is not true.
Okay. So, okay, so we are just making x 0 and then.
Yes, this is actually equality.
Mm-hmm.
You put if you if you that is the thing is that if you write explicitly, this will actually become this thing.
Okay, okay.
We are putting x equal to 0 left hand side and the right hand side.
So
We are getting this thing.
now there is a rule that says, supposing we have a matrix which we can break the column into two separate parts,
Yes.
then determinant of each part is equal to the determinant of the whole, right?
Yes.
So how is that different? Because here also we can write A minus xi as a single determinant, as a single matrix.
But this single matrix is not block matrix, right? This is not a some kind of block matrix.
Okay.
Okay.
Okay. Yeah.
Okay. So this thing you can also easily see that for this example, let us check this example. Here the trace is 1 plus 1, right? This is 2. And sum of the eigenvalue, this is also 0 plus 2, which is 2. Okay. So those are the important properties of eigenvalues. And let us see some other properties. So, eigenvalues of those classes. Let us consider real symmetric matrix and not real, it will be automatically real skew symmetric matrix, and other matrices are, for example, orthogonal matrix, and what those kinds of matrices are called. Those are called a square equal to a. These type of matrices are called idempotent, right? Idempotent matrix. And we can generalize this fact to a to the power n equal to a. So those are some important classes of matrices. Another matrix is nilpotent, and there is also complex analog, that is Hermitian matrix. For this, complex analog is Q Hermitian, and for this it is unitary matrix. So let us see properties of eigenvalues for those kinds of matrices. Okay. When we'll consider symmetric or skew symmetric matrices, then the field will be considered to be real number. Okay, for symmetric, skew symmetric, or orthogonal. And for other cases, here since complex number is already involved, the field will be considered as complex number. It will be provided in the question. You should look at what the underlying field is given. So the case number 1 is symmetric matrix. The interesting fact is that eigenvalues of symmetric matrices is always real number. Okay. So how do we prove that? So let lambda be an eigenvalue. Then this will be satisfied for some non-zero x. There exists x not equal to 0 such that this holds. And from here, if you do transpose, then you will get x transpose a transpose. This is same as lambda times x transpose. Okay. Now from here and from here, just multiply X transpose. Here multiply X transpose left hand side, multiply this X transpose time this, then it will get X transpose AX. This is actually lambda X. Okay, and this is actually same as, since A transpose is A, we are considering symmetric matrices, so this is actually X transpose A. And now here multiply X on the right side, then we'll get X transpose A times X. This is actually lambda times, sorry, we have not multiplied X transpose right hand side, so here also this is actually lambda times X transpose X. Now if we subtract those two things, then we will get 0, and here it is lambda times X transpose X.
So top also it will be X transpose. On the top
I have
equation,
done something wrong
yeah,
here.
in the first equation on the right hand side, it will be lambda X transpose.
Oh, okay. We have multiplied on the left hand side, and here we are multiplied on the right hand side.
Oh, okay.
So I have done something wrong here. We don't need to do those types of things here. We can simply. Okay. Sorry for this. Actually, we need to do this type of things, not transpose. We need to do conjugate transpose. Uh, sorry for this. Because we don't know if it is real or complex. If it is real, then the answer is already given, right? So it can be complex. Complex entries are also involved in the eigenvalues. We are doing this star. Since we are considering real numbers, star is actually same as this
Transpose.
transpose, and it A transpose is same as A. So here now we are using conjugate transpose. So lambda will be lambda bar, right? Because we don't know if lambda is real or not. If lambda is real, then lambda bar will be same as lambda. There will be no effect. So now subtract those two things. Okay.
So lambda is a scalar.
Lambda is a scalar from C. Okay. From the complex number.
Okay.
So that's why instead of transpose, we are doing conjugate transpose. Okay.
Yeah, I got it, but for taking only for X and A, right? But lambda was just a multiple of X.
Lambda is?
Just a multiple for X, which is a vector.
Let us check an example. Consider this matrix I times X. X is vector of this form, right? 1 times 2. Then what will be conjugate transpose of this? This is suppose this is actually lambda X.
Okay.
Lambda X star. This is same as I2 star conjugate transpose of this, and this is actually same as
Minus I.
minus I and 2.
Yeah.
But if you only do so, this is not actually same as lambda X star. I am saying that you need to take transpose here, then it will be same. Now you can see the fact.
Okay. Yeah, I'll try to understand. Please go ahead.
Okay. Let us do what is lambda times X bar. Lambda times X star. If you do lambda times X star.
So, sir, we are trying to prove that for a symmetric matrix, the lambda is always real, right?
Yes.
That's what we're trying to prove. So are we trying to take an example where lambda is complex and then trying to prove it cannot be complex?
Yes, yes. We are trying that. That we have taken lambda from the field C. So what I have said previously, actually, every field is underlying field is assumed to be complex. Okay. Otherwise, there is no meaning to this fact.
Okay, but like you started with saying that we are going to prove that lambda is always real.
Yes, yes.
Okay.
So here you can see that lambda time x star, actually this is I times 1 comma 2, and this is not actually same as this, right? You need to take lambda bar time x star. That is what I have written here.
Okay.
Okay. So now if you subtract, it will give where it is x star. Sorry, x star now. Everything is star. Subtracting this, we'll get 0 equal to same as lambda time x star x. Lambda minus lambda bar times x star x. And we know that x star x, this is actually non-zero, always non-negative, because x star x actually defined an inner product. Earlier day we have seen this fact. Okay. So this is, since this is non-zero, this will automatically imply that lambda minus lambda bar, this must be 0. And lambda minus lambda bar, so this says lambda is same as lambda bar. So when a complex number is same as its conjugate, that is a plus ib is same as a minus ib. When this will hold? What is the?
And there is no imaginary part.
Yes, there is no imaginary part. This will imply imaginary part of lambda. This is actually 0, because lambda minus lambda bar by 2. This is actually imaginary part of lambda, right? So that is what we have written explicitly. And from here, now we can say that eigenvalue of symmetric matrix is real. Okay. Now let us prove another fact. What will be an eigenvalue for skew symmetric matrix? For skew symmetric matrix, the proof will be almost similar, but here A star is minus A, right?
Sir, is it also true for symmetric that it always has the full rank? A is always full rank.
A is,
Like if A belongs to Rn, X
yes.
belongs to Rn, then A will have like eigenvalues will be the same number. It cannot be less. Is that true?
Uh, that is, there are indifferent eigenvalues. Are you saying
Yeah.
so?
Yes. Yes. Like it cannot be less. Is that like normally eigenvalues can be less than the dimension of the space, vector space, right?
Consider this matrix, identity matrix.
Yeah.
What what will be eigenvalues for these matrices?
Uh, Only one.
Only one.
Yeah.
Because because we can easily see that I minus lambda x, determinant of this equal to 0.
Yeah.
This
Lambda is equal to one. Mm.
same as 1 minus lambda, 1 minus lambda, 1 minus lambda. This determinant is 0. That is 1 minus lambda whole cube. This is 0. and this will automatically imply all eigenvalues are
1. Yeah.
1.
Yeah, actually, is the diagonal matrix, this one, is this also symmetric, considered symmetric?
Yes, diagonal matrix is symmetric because transpose, if you do transpose, then it will be
Okay.
remain same.
So, so it's not necessary that three eigenvalues are there. Okay, fine.
Okay, they may not be distinct. Yes.
Yeah, thank you.
And from here you can also observe the following interesting thing, that eigen values of an of a triangular matrix is diagonal entries. Sorry, are diagonal entries. And diagonal matrix is special case of triangular matrix. So that is why eigenvalues of identity, this is actually the diagonal entries 1 1 1. How do you prove that? Suppose A is this n by n matrix, A11, A22 up to ANN. For simplicity, let us consider A33 up to this. Let us consider this upper triangular matrix, upper triangular, and there will be some entries here. Uh, those are some entries. Let us not consider those, because now if you see this characteristic equation is determinant of A minus lambda I, or instead of lambda I, let us write xi. Okay, because we always for equation the variable is always denoted by x. That is why instead of writing lambda we are writing x. This is actually 0, and this is 0 imply A11 minus lambda. There will be some different terms, 0, A22 minus lambda. There is another term, A33 minus lambda. Determinant of this actually is 0. Now we know what is the determinant of an upper triangular matrix. It is actually product of the diagonal.
Yeah.
Because we'll expand with respect to this column, that is this times this. Now expand with respect to the first column.
Mm-hmm.
Okay. In this way, we'll get this determinant actually same as A11 minus lambda, A22 minus lambda, A33 minus lambda. This is 0. So we are getting lambda equal to the diagonal entries. Diagonal entries. Okay, so determinant. So for any upper triangular or lower triangular matrices, eigenvalues are always diagonal entries. Okay, this is also an interesting fact. Let us return to the problem. That is, what will be an eigen value of a skew symmetric matrix will look like. Instead of skew symmetric matrix, let us consider those skew Hermitian matrices. Okay, so skew Hermitian matrices are complex matrices such that A star is same as minus A. A is skew Hermitian. So this will imply A star x. So let lambda be an eigenvalue. Then there exists some non-zero x such that ax equal to lambda x. Okay. Then if you take the conjugate transpose, then this is actually x star, and this is actually lambda x star, and this is same as x star s star equal to lambda star. For lambda star, lambda it is actually lambda bar. You can thought lambda as 1 by 1 matrix. Okay, so conjugate transpose of lambda, then this entry will be, that is a plus ib. If lambda is a plus ib, then it will becomes a minus ib. So we need to take lambda bar here, and this is actually x star. Okay, so again multiply this thing with x star. Multiply this thing with x star in the left hand side, and this will give x star ax equal to lambda x star x. And from here, if you multiply x on the on the right side, that is this time x, then we'll get x star x equal to lambda bar x star x. But we know that a star is same as minus a, right? It is given. So from here, this is a star can be replaced by minus a. Now instead of subtracting as previous, we add those two things. Okay, adding this, we are getting 0 equal to lambda plus lambda bar into x star x. Again, since x is non-zero, x star x is always positive thing. Okay, because x star x is actually an inner product, and we know inner product is always non-zero, and given the vector is non-zero, the inner product will be positive. So that's why this will automatically imply lambda plus lambda bar actually 0, because x star x, this thing actually positive. Okay, this is square of something. This is actually norm of x square. So this will be automatically positive thing. So, and this is same as lambda plus lambda bar by 2 equal to 0, but this is actually real part. Sorry, this is actually real part of lambda. Hence, lambda is purely imaginary. That is, there is no real part. Okay, this is how eigenvector, eigenvalue of a skew Hermitian matrix will look like. And in a similar way, eigen value for skew, instead of skew Hermitians, if you put skew symmetry here, this will be also the same. Conclusion will be same, because the same thing is applied. Okay. Let us check another example. A is nilpotent. For this case, what is the definition of nilpotent matrix? There exists some k such that a to the power k, this is same as 0. Okay. Now again, assume lambda be an eigenvalue. Then we will get x equal to lambda x for some non-zero x. There exists non-zero x such that x equal to lambda x. And now apply another a, that is multiply a. So this x, so this will give a square x, sorry, equal to lambda times x. But lambda times x, this is same as lambda times lambda x by this definition. So this is lambda square x, and inductively we are getting a to the power kx. Here there will be x. A to the power kx is same as lambda to the power kx. And now use the fact a to the power k is 0. So this will imply 0 equal to lambda to the power kx. And from here we are getting lambda to the power k equal to 0 since x is non-zero. Okay, so this will automatically imply lambda equal to 0. Values of a nilpotent matrix is 0. So 0 is the only eigenvalue. Okay, and similarly for those kind of matrix a to the power n equal to a, those are for particular n, if n equal to 2, those are called idempotent matrix. So for this type of matrix, the eigenvalue will satisfy this thing, lambda to the power n equal to lambda. Just apply x on the both sides. That is, if you apply a to the power nx, this is ax, where x is eigenvector corresponding to lambda, then this side will be lambda to the power nx, this is lambda x. Do the same thing. This will imply lambda to the power n equal to lambda. Since x is non-zero, this will imply lambda satisfies this relation. That is lambda. So either lambda equal to 0 or.
Sir, first line we have a raised to n x is equal to ax. So
Yes.
can you please help understand? So yeah, is it that we have written ax is equal to a raised to n because a is equal to a raised to n?
From this, we have used this fact. This is actually given.
Okay.
We are trying to find eigenvalues of those kinds of matrices.
Okay, so after that, the RHS we have replaced with lambda x.
Yes.
On the LHS, how did we get a raised to n equal to lambda n?
Okay. For this fact.
Yeah.
For nx, so we have already assumed x equal to eigenvector corresponding to lambda. We have already assumed that.
Yeah, but a we cannot directly equate to lambda.
This is, you can write is as a to the power n minus 1 into x, right?
Okay. Yeah.
Then what is ax? By
Lambda.
definition, this is lambda times x.
Yes.
Lambda times a to the power n minus 1 x.
Okay. It will keep.
Now use induction. Okay.
Okay. I got it. Thank you.
This will give lambda times lambda to the power nx. And another interesting thing is that eigenvalues of orthogonal matrices satisfies this thing. Mod of lambda is 1. That is, modulus of the eigenvalues will be 1. Now if we are working over real field, then there will be only two possibilities. Lambda is plus 1 or minus 1. Okay. So most of the cases we will consider real field. The field, we need to see what the field is given. We need to check that. Otherwise the answer will differ. Okay. And similarly for unitary matrices, eigenvalue will be, modulus of the eigenvalue will be 1. So those are the some nice properties of eigenvalues, let us see another beautiful property. So it says similar matrices have the same eigenvalues. Okay. So what is the definition of similar matrix? A and B are said to be similar if there exists a non-singular matrix P. Okay, P is n by n matrices. We are considering n by n matrices. A, B are both n by n matrices. P is non-singular, such that B can be written as P inverse AP or PAP inverse, whatever you write. So those type of matrices will be called similar to each other. Okay, A is said to be similar to B and B is said to be similar to A, because you can also write A as P A P inverse, P B P inverse. Just take just multiply P and P inverse both sides. Okay. So the fact is the similar matrices have same eigenvalues. How do we check that? This is easy to check. Just a small trick. Determinant of P, sorry, determinant of B minus xi. We are considering that uh, that is we are considering the left hand side of the characteristic polynomial. This is actually same as determinant of, since B can be written as this, P inverse AP minus xi. Now you can see that this inner part, you can write this inner part as take P inverse and P common. Okay, and this is actually A minus xi. Just multiply those two things and distributive property will give the inner part, right? Now determinant is multiplicative, so this is same as determinant of P inverse times determinant of A minus xi times determinant of P. Okay, so from here this thing equal to 0 if and only if this whole thing is 0, but determinant of P inverse is non-zero because P is non-singular already given. So this is 0 imply 0 is same as determinant of A minus xi. Those are if and only if. So from here clearly you can see an eigenvalue of B will be an eigenvalue of A. Okay, so this is the proof. Is it clear?
Yeah.
Let us see some exercise from the book. So the given matrix is 0 0 0 0 A 0 0 0 0 B 0 0 0 0 C 0. This is the given matrix T. Okay. The question is, what are the eigenvalues of T? Eigenvalues of T. you can easily see that this is actually lower triangular matrix, right? So for lower triangular matrices, eigenvalues are the diagonal entries. So only the eigenvalue is 0 here because all the diagonal entries are 0, right? Let us see another example. So before this is actually exercise from the book. This says prove that I minus AB invertible if and only if I minus BA is invertible. Okay. So this is the question. How do we prove that? Before proving that, let us see an interesting thing. So you know that 1 minus x inverse, this can be written as 1 instead of x. Let us write small ab. Inverse of this, we know this can be written as 1 plus ab plus ab whole square plus ab whole cube up to it will continue. Okay, this is true when mod ab is less than 1, otherwise it is not true. It may not be true. It is not true actually. This is our assumption. So now if you separate one and if you take a and b common, then this is actually same as take a and b common here. So we are uh, we are considering those terms only. So because what is ab to the power n? This is actually ab times ab. It will continue up to n times, right? If you take a common in the left side and b common in the right side, then it will be pair will be ba and ba. Okay, so ba times ba up to ba. So this is same as a times ba to the power n minus 1 times b. Is it okay? So here this will look like 1 plus 1 power will be decreased because we have taken a common in the left side, b common in the right side. From here we have used this fact. Okay, this is an interesting fact. This trick will be used many times, so you should remember this trick, and this will continue. And now you see this is actually 1 plus a. Now what is 1 plus ba square up to continue? What is this thing? This is actually 1 inverse of 1 minus ba, and this is actually b. Is it okay?
No, sir, it's not very clear, but I'm just trying to understand what's going on.
We have just manipulated. We have done nothing. This is actually from the formula. We know this thing, right? Inverse of 1 minus x, power series of this. This is 1 plus x squared. It will continue. We have written this thing.
Yes.
Now we have separated the first one.
Yeah.
And we are taking common from this ab to the power n. We are taking common a and b in the left side and the right side.
Yes, sir, but on the left what you are showing this in the square brackets, that is a multiple, but on the right hand side what we have, that is a sum of like ab plus ab square plus ab cube, like that. That is a sum, right?
Yes, we have just used distributive property.
Okay, so we just took out ab in a
Yes,
way and kept
away
a.
from everything.
Yeah, and so the inner series becomes a,
Power series.
1 minus AB BA inverse. Okay.
Yes.
Okay. Hmm.
So here it is very easy because here it is actually clearer because 1 minus AB and 1 minus B are the same thing.
Yeah.
Okay.
Hmm.
But for matrices, we don't know if they are same or not. They can be same or they can be distinct matrices.
Hmm. Yeah.
So the important thing from this observation, the since one thing is invertible, another thing we need to prove it is also invertible. Our guess will be inverse of another thing. This is our guess
Hmm.
from this formula. This will look like identity plus we are using this thing of uh, identity plus we have just replaced a and b. This is b 1 minus 1 is now identity minus ab inverse times in, times a. We have interchanged the role of ab.
Hmm.
So this is our guess. So we need to prove that if this thing is invertible, this is given to you. We need to. There is two way to prove something is invertible.
Yeah.
Either do some operation or do something and conclude that it is invertible, and other way is find inverse of this. We are doing the second way. Okay, we are finding inverse of this.
Yeah.
So let us return to this problem. Proof. Let I minus AB is invertible. Okay. So assume this to be x. This is invertible. We need to prove I minus BA is also invertible. So the idea is to multiply I minus BA with it inverse. Okay. So our guess was I plus B times I minus AB inverse times A. We need to prove that this is identity. Then it will be done. Right? We are proving this thing is invertible. So we need to find a matrix such that multiplying with that matrix gives identity.
Yeah.
We are trying to prove that this thing.
Hmm. Hmm.
Okay. So this is actually some algebra. We need to manipulate those things. If you multiply, this is I minus AB plus another thing will be I minus AB. Sorry for this. Multiply with first identity, this will give I minus BA, and the second thing it will be I minus. Instead of writing this, we can write it in simple form. This is B, this is X inverse, this is A, right? So this is I minus BA times B X inverse A. Okay, is it clear? We have just used the distributive property up to this. Again, this is I minus BA plus B X inverse A. Again, we are using distributive property. B A B X inverse A. Right? Now we need to do some kind of manipulation here. This is the most important Wait. So take I here. Now the remaining thing will be, if you take B and A common, because there are B and A on the left and right side, then take B common in the left side, A common in the right side. Then the first thing will be identity, and next thing will be X inverse, and here it is actually AB X inverse, right? And the next step will be I minus B, I plus, now again take X inverse common here. So it is I plus AB. I have done some mistake for notation, right? There is some mistake. It is actually minus. So there will be some minus. If we take minus common, then it is actually I minus AB times X inverse into A.
So minus I होगा the first,
Minus I over
because it was minus BA in the beginning, no? So we took B to the left and A to the right.
minus B times A. It is
Yeah.
minus BA.
So
Then,
that's what. Oh, a minus is outside still. Okay, okay. Yes, yes. Got it.
okay. So this is fine. So now you see this I minus AB, this is actually X, right? This is same as X. So what is X times X inverse? This is actually X. So X times X inverse, this is actually identity. So this is, we are getting I minus B times identity minus X times X inverse, that is again identity times X. So this part is 0. So we are getting, is it okay?
Sir, just a minute. I'm just trying to catch up. So I minus AB is equal to X. So X into X inverse is I. Okay.
There is some manipulation. You need to be careful here. Okay, otherwise, most often you will do something wrong. Here, you need to be careful because this is the main step, taking B and A common. This is the main step for this.
Yeah.
If you don't do this, you will not get the answer. So this is the interesting fact. If I minus AB is invertible, then I minus BA, the opposite thing is also invertible. And similarly, the converse is same. If you assume this invertible by symmetry, right? Just replace A and B by B and A. Then this will imply this. Okay, so proof is done. Now let us prove another thing. This question is also from the book, which says A and B are n by n matrices. Then show that eigenvalues of AB is same as eigenvalues of BA. We need to show this. So what is the way? Let us check this. So let lambda be an eigenvalue. Value of A. Okay, don't assume. Let us write this. This will automatically, this is true if and only if
AB minus lambda I is equal to 0, determinant.
yes, determinant of this actually 0. Okay, so instead of assuming this, let us assume the reverse part, that is, let lambda is not an eigen. Okay, then determinant will be non-zero, right? Lambda is eigenvalue if and only if determinant is 0. So now we can use this fact. Okay, eigenvalue of I minus ab, determinant of I minus ab. If we use this fact, actually we can conclude that determinant of ba. So you can use this fact instead of I minus ab. You can replace lambda I here. Okay, and you may prove determinant of this uh, one is invertible if and only if another is invertible. Instead of I minus ab, you can put lambda I minus ab here. Okay, and actually this means ab minus lambda I is invertible. By the previous fact, we are getting ba minus lambda I. This is also invertible. By the previous fact, we have just proved, and this will imply determinant of ba minus lambda I is non-zero. This will if and only if lambda is not an eigen value of ba. So the eigenvalues, the if lambda is not an eigenvalue of AB, then lambda is not an eigenvalue of BA, and reverse is also true. So from here you may conclude that eigenvalues of AB and BA are same, but note that lambda actually, the fact is lambda is non-zero here. We have considered lambda to be non-zero. That is non-zero because here we have assumed lambda is non-zero thing. Okay, then that non-zero thing will not be eigenvalue of BA also. Because for this fact, this if and only if this AB minus lambda is invertible, if and only BA minus lambda is invertible, this fact is, we have proved this fact when lambda is non-zero. Okay, for here we can replace I by some lambda when lambda is non-zero. So we are using this fact here. That's why we are not assuming zero eigenvalues. And now the general fact, so non-zero eigenvalues are same, and AB and BA both have same number of eigenvalues, right? Because AB and BA both are n by n matrices, there will be n eigenvalues. So non-zero eigenvalues are same. This, then the remaining zero eigenvalues, this must be same, because there are, suppose there are k non-zero eigenvalues, so those things are same. AB has the eigenvalues a1 up to ak, and BA also has those eigenvalues. Then remaining ak plus 1 up to an, those are zero eigenvalues. Then remaining eigenvalues of BA, this must be zero, right? Because there are n minus k remaining things for AB and BA both. Okay, so this will automatically imply all the eigenvalues of AB and BA are same. Okay, this is an interesting case. Let us do another. This is an interesting problem. Here the operator is given by this integration operator. We have already know about, it is already known that V given V is the space of all continuous functions. We are considering this vector space. Okay, space of all continuous functions. You can add two continuous functions, this will give continuous function. You can multiply with some scalar, this will be again a continuous function. So continuous functions form a vector space. Okay, now define T from V to V by T of some f. This will be an continuous function. So the continuous function is defined by integrate this thing 0 to x f to dt. Okay, so TF is continuous function in the codomain, and at a point x, this is the same as this integration. This is the definition of the linear transformation. Then we need to prove that T has no eigenvalues. We need to prove this fact. So how do we prove that? So this is also an interesting example. Okay, so for finite matrices, we know that there will be, for n by n matrices, there will be n eigenvalues. Okay, but for infinite dimensional cases, there may not be a single eigenvalue. This is the interesting case, and this example shows that fact. Because here V is not finite dimensional space. The vector space V is now infinite dimensional space, and for infinite dimensional space, there may not be a single eigenvalue. Okay, there are some transformation like this for which there is no eigenvalue. Okay, so how do you prove that? The proof is like this. Let lambda be an eigenvalue. Assume on contrary to that fact, then Tf, this would be same as lambda time f, and now if you apply Tf on x, case 1, similar to the previous, assume lambda is non-zero. We need this thing. This is same as lambda f times x, but Tf, this is defined by 0 to x ft dt. It's the same as lambda fx. And if you differentiate with respect to x, differentiate with respect to x by Leibniz rule, this is actually fx, left hand side, and the right hand side is f dash x. Though the space consists continuous functions, but here the left hand side is differentiable. Okay, you can check this thing, why is it differentiable. So this will imply the right hand side will automatically differentiable. That's why we can take differentiation of f. Okay, now so this is equivalent to this with the condition.
Sir, what is f hyphen? Like
This is df dx, right?
f hyphen is df dx?
Yes, f dash denote df dx. So you can see f of 0 is also 0, right? Just take the limit to be 0, then the left hand side is 0 and f0 is 0, because we have assumed lambda to be non-zero.
Sir, we have differentiated this equation on both the sides.
With respect to x.
With respect to x, okay.
Yes.
So there is already an integral. If we take that, then it will become f of x.
Yes.
Plus f of 0, right?
Yes.
So now df of x by dx minus d0 is by dx is equal to lambda f prime.
Yes. Actually, you can check this fact. This is an interesting thing which is proved during real analysis. Okay. For integration, d dx of this integration 0 to x 50 dt, this is actually fx itself. This is an interesting theorem in real analysis. This is very, very interesting. You can prove using partition, all those things. Riemann integral. Okay. Or otherwise, if you are not comfortable with this, just blindly apply that
Integral.
Yes.
Okay. Yeah, actually not very clear like how we got this, but if we apply integral, still we will get the same thing, I think.
Yes.
Okay.
This says that integral then differentiate, this will give the same thing. This is the main story behind this theorem.
Okay.
So those two things are equivalent. Now the fact that you cannot solve this, okay, because this is same as y equal to lambda time dy dx. Just for simplicity, assume fx to be y. Okay, so first equation 1, this is actually given by this thing, and now dy by y, this is lambda dx. Integrating, we are getting ln y is same as lambda x plus some constant, and y is another constant, c does another constant time e to the power lambda x. So this will imply fx equal to c e to the power lambda x. But the second thing gives f of 0 equal to 0. So clearly those are not consistent. Those, because this 1 and 2, from 1 we are getting f of 0. This is c e to the power 0, which is c. Okay, and from the second we are getting f of 0 equal to 0, right? uh, uh, there are some sorry for this. This is actually dy by y equal to 1 by lambda dx. This is 1 by lambda x plus some constant, and this is c e to the power lambda x. Here you can see that c cannot be 0 here, because how do we get c? C is actually, c comes from here actually. The explicitly this is 1 by lambda x plus c dash plus c. Let us write in this way. So the solution is given by like this: e to the power x by lambda plus some c. But here this is actually e to the power c. From equation 1 we are getting e to the power c. From equation 2 we are getting f of 0 equal to 0, and those two things cannot be same. Exponential of anything, this is always positive. Okay, so this imply that this one, not one, this star has no solution, right? That is, star is equivalent to this thing. Star is equivalent to this double star. Okay, this star, and this will automatically imply this double star has no solution. Okay, so there is no such lambda. Therefore, there is no such lambda. If there is some lambda, then it will create an issue. It will contradict the fact e to the power c is non-zero. Is it okay up to this?
Yeah.
We have just taken the we have just used that differential equation, and we are getting the solution to be this. But if this is the solution of the first equation, this will contradict with the second fact, that f of 0 to be is same as 0. Okay, that is why uh, there are no such lambda for which tf equal to lambda f. Okay, now case 2, what happens when lambda equal to 0? Then tf equal to lambda f. This will give lambda f is 0 then, but by definition t of fx equal to 0 of x. 0 is the continuous function, that is 0 everywhere. Okay, so t of fx equal to 0. By definition, this is 0 to x ft dt, which is 0, and this will again apply derivative. This will imply fx differentiate with respect to x. Okay, by this definition, we are getting fx equal to 0, and this is true for all x, and this imply f is identically 0. But we all we know that eigenvalue is eigenvector. We have assumed f to be eigenvector, and we are getting the eigenvector is 0. This is again a contradiction. Okay, because this f is already assumed to be non-zero. When we are assuming lambda be an eigenvalue, then there exists some non-zero f such that this holds. So we have already assumed f to be non-zero. So then again we are getting a contradiction. Therefore, lambda equal to 0 can't be an eigenvalue. Up to this, is it okay? So for both cases, there are some contradiction.
Sir, can you explain in some other way, like geometrical way, what it will mean? This thing.
Here, geometry is not very obvious because this
Mm,
case is completely abstract.
mm.
But
Just some simple example.
simple example. So instead of continuous functions, let us do a simple example. So instead of continuous function, let us consider this case. Space, let V is now space of polynomials. All polynomials.
Okay.
And what T is doing? Take an polynomial a0 plus a1x up to an x to the power n. Then from the previous definition, this is integration of this thing, right?
Mm-hmm. Yeah.
N t to the power n
Mm.
dt. And if you uh, do this, this will give a0x a1x square by 2 up to an x to the power n plus 1 by n plus 1. So from here, you can see that from here you can see that there is no x such that tx equal to lambda x, right? Tx equal to lambda x.
Yeah.
There does
Yeah.
not there is no lambda such that this holds for some non-zero x, right?
Mhm. Yeah. So what you're saying is like, just I'm trying to say you can confirm. So what you're saying is earlier we used to take one vector.
Yes.
Now it's a polynomial space. So we cannot isolate a lambda which will multiply this whole polynomial in such a way that like it will become a lambda for right for the equation.
Yes, yes. You
Yeah.
can see there are shift of powers, right?
Mm-hmm.
If you try, let us see what is wrong if we try to do this. So assume t of this vector, t of x equal to lambda times x. Okay. Instead of x, let us denote it by v. Otherwise, it will be confusion. T of v equal to lambda. V is non-zero. So left hand side will get this thing a0x plus a1x square by 2 up to an x to the power n plus 1 by n plus 1. And the right hand side, we are getting lambda times a0 plus lambda times a1x up to lambda times an x to the power n, right? Now if we compare the coefficient, we are getting lambda is a0. There is no constant term on the left hand side, so lambda a0 is 0, right?
Yeah.
Now lambda a1, so lambda a1 coefficient of x, left hand side the coefficient is a0. This is a0, and inductively if you continue this, we are getting lambda an. This is actually an by n plus 1. So first case, assume lambda is non-zero. Again, if you assume lambda non-zero, then we get a0 equal to 0, then a1 equal to a0 by lambda. Again, a1 is 0, so
Which is
all an are 0. Okay.
Since they are not zero, so lambda is itself not
Yes.
possible.
But all a0 up to an are 0. This implies v, that vector a0 1 plus this thing. This polynomial is 0, right?
Yeah.
But we have assumed for non-zero v here. We are getting some contradiction.
Yeah. Yeah.
Similarly, if you assume this thing tv equal to lambda times v, if you assume lambda to be 0, then again we'll get contradiction, because now tv equal to 0, like this thing lambda a0, sorry, tv equal to lambda v, sorry, tv equal to lambda v is 0, so this will imply lambda a0, but what is actual tv? Sorry. Tv is the previous thing. This will imply a0 x plus a1 x squared by 2 up to n x to the power n by n plus 1. This is actually 0. And again, comparing the coefficient from the left and the right side, we are getting each ai is 0. Right? This will again imply v, this polynomial is identically 0. So again we are getting a contradiction, because we have assumed that v is non-zero.
So this means lambda does not exist.
Yes. So for the restrictive version, it is clear, because we are only considering the polynomials, but here this is actually generalization of this fact, because instead of polynomials, we can consider continuous functions also.
Okay.
Even for this case, there is no eigenvalue.
Okay.
So is there any question?
No, sir. Actually, two. One is from the assignment, last assignment which we started. That one. One is from one of the lectures. I have one question.
Okay, what is that question?
Okay. So in the lecture 34, sir is saying that. Uh, so I'll just read out the transcript.
Okay.
It is saying, just a second. Because it is diagonalizable, eigenvector corresponding to, he's talking about symmetric matrices. So I'll read little bit from above. Hold on. So because it is not very, some context should be there. Or I'll just play. I don't know if you can hear from my.
No, I can't. So, is it saying that matrices are diagonalizable? Is it the question?
He's telling that, okay, he's telling because it is diagonalizable, eigenvector corresponding to the distinct values are mutually orthogonal.
Okay.
Then he's saying inside, but inside, so till here I kind of assume like, okay, because metric matrix is diagonalizable, the eigenvectors corresponding to the distinct he has used the word distinct eigenvalues are mutually orthogonal. Okay, fine. The vectors are orthogonal. Okay, fine. Then he says, but inside each eigen subspace, the basis exists, but it may not be orthogonal. That line I didn't understand. Like you are,
Yes,
can I?
orthogonal for distinct. That is, he is saying that corresponding to lambda one.
Hmm.
Suppose you are getting an eigenvector v1. Okay. So
Can
corresponding to lambda one, suppose we are getting eigenvector v1.
sir, sorry, just 1 minute. I'm just going to like paste the text.
Okay, I have understand your question.
Acha.
I'm trying to give the answer. So,
Hmm.
corresponding to lambda one, we are getting an eigenvalue, eigenvector v1, and
Yeah.
corresponding to lambda two, we are getting two eigenvectors. Suppose one is
Hmm.
v2 and another
Hmm.
is v2 dash.
Hmm. So he's
So,
telling that
yes,
V1 dot V2 is 0, V1 dot V2 dash is 0, V2 dot V2 dash is 0. That he's telling,
so
right?
saying telling v1 and v2 is zero, and this is also zero, right?
Yeah, everything is mutually perpendicular,
Okay, okay, okay.
right? Then
Uh,
he's saying, but inside each eigen subspace, the basis exists, but it may not be orthogonal.
uh, Actually, he is saying that V1 and V2, this is actually zero. Another V1 and V2, this is also zero.
Yeah,
Those two things hold,
yeah.
but he is not saying that V2 and V2 dash is,
So when he says eigen subspace, he mean V2, V2 dash.
yes, yes.
Mm.
Eigenvalues means subspace corresponding to lambda 2.
Oh, okay, okay, okay. So that is what I didn't understand. So eigen subspace is the if one lambda has multiple vectors, then those constitute the subspace, eigen
Yes,
subspace.
those will constitute the eigenvalues. But we need to take zero also, include zero.
Okay, okay, I got it now. Okay, that was one thing. And then the third thing I wanted to ask, sir, in 2 weeks we are going to have exam.
Okay.
Just I just want to ask a very basic question. What is the structure of the exam? Like how many marks, question will come, and all that. Like what is the categories of questions?
Uh, I don't know about that. Can you look at the previous year's
No,
exam
sir.
structure or
I tried to Google today. Nothing. I got not even a single paper on the net.
okay?
Not And many people have written that it will be like the assignments, this, that.
Yes, I think it will be. It will the exam structure will look like the assignments. Uh,
So it will be all multiple choice. Like, I don't like so much 3 hours
uh,
exam, all multiple choice.
I think it will be all multiple choice
Hmm.
because for
Suppose,
NPTEL MCQ are preferred.
hmm,
I think all the
nothing,
papers will be.
no proof and all will not come for us.
Uh,
Proof, proofs and
it will not come. I think so. Can you write? Can you ask this in the chat?
no, no, I can write, but I don't get answers on the like very late answers that we will get like after 1 week, 2 week, and already exams are coming.
Okay. There is
Uh,
a person for those types of query. He
okay,
usually
okay.
reply to.
Hmm. Okay. Sir, so eigen subspace is the is the vector space for one lambda, right?
Yes, yes. For one lambda. For other lambda, they may not form a eigenvectors, eigenspace, a subspace.
Okay.
We need to take single lambda.
So he was saying, like if the for symmetric matrix, all the vectors are mutually orthogonal set. They
Yeah.
form the vectors form mutually orthogonal set. But now he is contradicting, saying that this can also happen, so it may not be a orthogonal set. So I think slowly he's like changing his statement. I think.
Okay. I think he has done some mistake in the previous step. So he's trying to say that though this is zero, but inside this lambda 2, they may not be zero.
Yeah.
He's
I got.
confident that.
Okay. Thank you so much. Yeah. Thanks.
Well, bye.
Bye.